Okay, so here we have a very introductory moment of inertia problem. Let's, of course, as always, read the problem statement first. Determine the moments of inertia, and the S there stands for Ix and Iy. Often when I give a problem like this on the exam, students just calculate Ix or Iy, and they forget that they have to calculate the moment of inertia about both axes. And then, notice that it's an I-beam here in this case, and it's a double symmetric I-beam. And that means that you already know where the centroid location is. So this is a very first problem, so I'm not going to make you calculate the centroid location because you already know that it's here due to symmetry. In fact, let's write that down. So due to symmetry, centroid location is known. And in fact, it's already given in this picture, right? So you know it's already half the height and half the width. Another thing that is nice for us here due to symmetry is that the top half is kind of equivalent to the bottom half, or the right is equivalent to the left. But that is something that should not be of interest to you right now. That is something that will help you later on. But right now, because it's an educational problem, I just want to focus on how to calculate my formulas or how to fulfill my formulas. So the first thing I usually do when I write these problems is remind myself that I have to take the sum of Ix bar prime plus AI dy squared. So that is my first formula. My second formula is Iy is equal to I bar y prime plus AI dx squared. And so last thing left to do is to understand how we can use this. And remember that here we're talking about AIs, so individual areas. So my first job is to discretize the cross section, which of course here is already done for you. So there's not a lot of mystery left here. So let's pretend that I have a shape A1 here. So A1. And then maybe I have a shape down here, which of course is the same, but for educational reasons is A2. And then last but not least, I have this one here, which is A3. And now I will try to show you how I fulfill this component and these components for each individual shape. And I tell you up front that a lot of professors or a lot of books even recommend that you should use like a tabulated method. Once again, I think for a shape like this, a tabulated method is a waste of time. There's nothing wrong with the tabulated method, but to really understand which component goes where, I'm going to stay away from this here in this lecture. For your homework, you can of course use that if you want to, but for understanding purposes, it's better to look at it from an analytical standpoint and not from a plug and chug standpoint. So how do I fulfill my formula now? Ix, I'm going to focus on this formula first. Remember that this component here has something to do with base height cubed divided by 12 for a rectangle and so on. So I need to apply that to my area number 1. So let's do that. And what is my base for that area? My base is 200 and my height is 50 millimeters, and that needs to be cubed and divided by 12. So that comes from the table, and I now completed my first portion here. Now my next portion is the AI and the distance. The A, of course, is easy for everybody. So that would be 200 times 50. And now I need some lever arm. So what is the lever arm? Remember what dy is. Dy is actually the distance between the centroids. So I have a centroid here, the total centroid, and I have a centroid here. I'm going to draw that in there for you. So there's my C1. And then I also have a C total, which is right there. C total. So now how do I calculate the distance? I would argue that the distance there would be 300 divided by 2 plus 50 divided by 2. very important, not forgetting to square it, right? And so this completes my entire first area. And I say that again. So AI is easy, 200 times 50. The distance now is the distance from here to here in the x direction. And so that's 300 halves, because that's this distance divided in 2. And then 50 halves, which is from here to here. So I can finish that now. Next up, I have to add my next area element. And if you have a sharp eye, you already say, hey, it's exactly the same as this one and you are true. But again, this is an educational problem. So I want to use this as an opportunity to explain something very specific to you about this area, which actually is in the negative y direction. So let's do it anyways, although once you are familiar with these problems, you don't need to do that anymore. But base is 200, 50 is the height, cubed divided by 12. And now my area is still 200 times 50. And what is my lever arm now? So there's a C2 here. And the distance, of course, is from here to here. And that would be a distance of 300 halves plus 50 halves. But technically speaking, this would be a negative distance, right? Why can we still ignore that? Because we square it here. So you see that this formula here allows us to use negative numbers here and ignore the fact that this is actually in a negative direction. So this is different from when you calculated centroid locations of shapes. Then you have to really worry about positive and negative in your formulas. Here you don't have to worry about it, because a negative value squared will always give you a positive value anyway. So this purple part here is exactly the same as this part, but again, I wanted to get that educational point across. So I'm going to do that. Last but not least, I also have to include my blue area here. So let's zoom out a little bit. And I have to add that as well. What is the base now? So the base in this case is 50, right? So the base times height. The height now is 300. So 300 cubed over 12. And now plus the area, which is 50 times 300, multiplied by, I'll let you guess that for a second, what goes in here. I definitely have to square it. And what really goes in there is actually 0, right? Because the centroid of A3 coincides with the total centroid of the entire shape. So I actually gonna plug in 0 here. And that means that this entire part here goes to 0. So I don't have to worry about that. And hopefully that makes sense to you. I repeat it one more time. So the centroid of the entire shape of C total coincides with the centroid location of C3 or A3 centroid location. So that now is all my components. And notice that here I use the summation, right? So remember what I said earlier, that if you just sum up this part and this part and this part, you would not get your final answer, because you're completely ignoring this part, which is the parallel axis theorem part, and here as well, which actually adds a lot of stiffness. So I invite you to actually calculate this value and then calculate this value, and you will see that this value most often has a much higher contribution. In fact, there are some engineers out there who don't even worry about this part. They just use the area and take the distance and square it, just because it's conservative, and this is percentage-wise very little compared to this. And the larger the cross-section becomes, the more significant this becomes. However, you want to know the result for this. So let me tell you the result, and keep in mind that we of course always use 4 significant figures, and that we have super large numbers here and strange units. So the answer is 7,292 times 10 to the 5 millimeter to the power of 4. And I'll be honest with you, this is something that is very difficult to develop a feel for, like if this is right or wrong. It's not a number that you see often, or something you can really develop a feel for unless you calculate it many, many times. but maybe even one mechanics class is not enough to do that. So the best way to get a feel for it, or to counterbalance that you don't have a feel for it, is actually find another way to break this down into different sections and calculate your Ix in an alternative way. So another way that you could do, for example, is you can calculate an entire rectangle and then subtract this rectangle and subtract this rectangle, because keep in mind that a summation can also be a negative summation, right? So you can have the entire rectangle and subtract something. However, I promise you that this is the right answer for now, and we can move on to IY to continue with our educational experience here. So how do I calculate now IY? I encourage you to pause the video and calculate it for yourself or give it a try. I, of course, will not wait for that. I'm just going to continue now. So for my A1, base times height now, or actually height times base cubed. So that would be 50 times 200 cubed divided by 12. And that is my individual moment of inertia. Now I need to add the area. So 200 times 50. But now what is the distance, right? What is the distance from the total centroid, the green part here, C total, to C1 in the x direction, right? Keep in mind that we're using here dx. What is that distance? That actually is equal to 0 once again. So 0 here squared. And so this entire thing goes to 0. And now, because we already been through that learning experience, I can tell you that the next part, A2, is exactly the same. So I'm just going to multiply this by 2. And last but not least, I have to add my A3. So which now I have to, of course, look at it pretty much in the direction of the x-axis. So my base now is 300 and my height is 50. So 300 times 50 cubed divided by 12. And then plus area times 0 again, right? So this goes to 0 again. Once again, the centroid locations coincide with each other, so this goes to 0. So I don't have to worry about that. And now the final numerical answer for this would be equal to something that better be smaller than my Ix, because you can already tell that this has a very strong axis, strong resistance about bending about the x-axis, whereas about the y-axis, the material is not far removed from it. So therefore, it should be a smaller number. And you should see this in many problems that you solve like this. In fact, you're actually looking at 697.9 times 10 to the 5 millimeter to the power of 4. And now I solved the entire problem. Of course, I have to double underline my results here. And I am done solving that. So let's take a final look at it. I think now it should be clear how I calculate my I bar x prime, my AI, and what my dy is. And this is the one that is the biggest challenge for a beginner. And another challenge is to not forget the squaring component here. Here I did not square my 0 here, of course, for legal reasons. I guess I should just put it in there so you cannot sue me. But obviously I didn't need it anyways. However, it is my experience that students like to forget this. Well, they probably don't like to forget it, but it just happens. So please sharpen your senses for that component. And I think this problem now we solved, and I hope that all your questions have been answered for a simple structure like this, or a simple cross-section like this. And of course, we will now look into more complicated ones, or we will increase our difficulty level a little bit and introduce also different shapes. So here we have a problem that's maybe a little bit more interesting and a little bit more challenging. And more challenging is more interesting, right? So therefore, we can expand our knowledge about the moment of inertia and try to see if we really understand how to move forward with this. First of all, let's look at the problem statement. We need to calculate Ix and Iy for the concrete barrier. I'll be honest with you, these dimensions here are not conducive towards concrete, for sure not. Like, it would be way too small for like a real concrete barrier, but the concept still applies. So for a real concrete barrier, probably this would be more in dimensions of feet or something like that. However, to get the educational point across, we can easily do that. Note that this problem also asks you the centroid location must be determined first. And we have done this in a previous example, so I'm just gonna put that information in here. I believe we had this to be calculated somewhere right there. And I believe our value was something 2.5. Let me look that up for you. But first, I'm gonna put this information in here. So we calculated this with y bar. So we have y bar here, and that was equal to 2.565. 2.565. And that will teach us something very valuable when we talk about dy and dx and so on. Notice also that the centroid location coincides with the y-axis, so I do not need to calculate anything else than the y bar. So I don't need to calculate the x bar, but we talked about that in that lecture. All right, like we did in the centroid lecture, we also have to section our element now into area elements that are of known shape and known geometry. And I believe we did it so that the horizontal part on the bottom is actually continuous. So I'm gonna do that here as well. And then I have my different areas. And I believe this here was our area 1. So I'm gonna call that A1. And then I have an area down here, which I'm gonna call A2. And then I believe we named these here A3A and A3B. So I'm going to do that here again, A3B. Now notice that each one of them has a centroid location. So this one here, for example, has a centroid location right there. Then there's a centroid location right there. And we have in the third points. And I'm just symbolically showing these here. I will, as I go through the calculation, refer back to them. But before I do that, let me point out that what we really need, for example, for A1 is the distance from here to here, right? And I will show you a trick of how you can get that very easily and very reliably without using a lot of brain power. So how do you get the distance from here to here? You can easily structure that approach. As always, I start with my formula. So if I have to calculate Ix, I usually have to find the summation of I bar x prime and AI dy squared. And I also have to do that for Iy. So the summation of I bar y prime plus AI dx squared. And now with that said, again, it would probably be suitable for a tabulated approach here, but to me, it's still not enough shapes to actually use a table. A lot of people prefer a table method. I do not, unless I have a very big structure that has a lot of different shapes. This here has only like a maximum of 4 shapes. I don't even bother. It takes too much time, especially on an exam. I would waste too much time setting up my table and thinking about what to fill into the table instead of actually completing these equations. So let's start with Ix. Ix is equal to, for shape number 1, base times height cubed, right? So what is the base? That's 1 inch. And the height, be careful, is 7.5 cubed over 12. Plus the area, which is the same, 1 plus 7.5. And in fact, I said the same because I developed a habit over the years to just set this up with a lot of brain power, and then this I do blindly by just copying what's going on here. And that's why I said it's the same. But now the lever arm is what? The lever arm is the distance from the centroid of the individual shape to the centroid of the total shape. And so I will make my life easy, actually. I know that this here is 7.5 halves, right? So remember that I have this distance here, which is 7.5 over 2, which is equal to 3.75. So that 3.75 is also true on the bottom part. So I'm just going to now move from here all the way down, and then I subtract this part. That will make my life much easier than actually using a lot of brain power. So 7.5 divided by 2 plus 1. Where's that 1 coming from? I have to, like right now, I went from here to here, and now I need to add the 1. And then I need to subtract this. So minus 2.565. Of course, I cannot forget to square this, otherwise I'm in trouble. But now I'm done with my part number 1. So let's move on to part number 2. Plus base times height. In this case, it's 6 wide. And the height is 1, which needs to be cubed. Of course, has no impact here. Divided by 12. Plus my area, which I can once again copy blindly, 6 by 1. And now the distance, I'm just gonna go 0.5 minus 2.565. And yes, this is a negative number, but remember, I can just square it and I don't care about this. So what did I do here? I moved from the centroid location down, and then I subtracted this, which is the same as taking the inverse if you don't square it. So like 2.565 minus 0.5. And maybe in this case, it would be very simple to do that. But I want to give you this approach because later on, you may find very complicated structures where you have to add like 3, 4, 5 directions or distances to each other and then subtract it. And this method always works. So I would always go from the point that I want down to the reference axis and then subtract that value. Okay, now we can use our A3A. And what is that? So now we're using a rectangle, sorry, not a rectangle anymore, but a triangle. So what is it? Base times height cubed divided by 36, right? So the base here is 2.5. Be careful about that. It's not 3, it's 2.5. Why is that? Because from here to here, I need to subtract the 0.5 here. So 2.5 times 1.5 cubed divided by 36. This is important. This is because it's a triangle. Plus the area, which is 1/2 times 2.5 times 1.5. And now my lever arm is what? So I have to move from here down to here. So I would say 1/3 of 1.5 plus 1, and then subtract the lever arm. So let's do that. So 1/3 times 1.5. And to stay with my colors here, plus 1 and minus 2.565. And then the whole thing squared again. And now I have defined my entire A3A. And what you will notice that we're taking IX, and so this distance here goes down in this direction, and therefore my A3A is identical to A3B. So I don't have to do anything else but multiply this by 2, because I am only interested in the vertical direction. Remember, this here is dy, right? So maybe I should put that in there as well. So this here is dy for shape number 3. And so therefore I just multiply it by 2. And if you do that properly, you will find, and I encourage you, by the way, to really try to type these things into your calculator, because in an exam situation, it's always critical to do this in a timely fashion, and it's very easy to mistype anything here. So I really recommend that you try these in a real life situation with typing in and checking your own mistakes and so on. but if you solve this correctly, you will find that it's 101.8 inch to the 4. And this is the result, so I double underline it. And that concludes my IX. Now let's take a look at our IY. So that is the moment about the y-axis. So IY would be equal to, now my base times height changes, right? So my height now is in this direction. So base is 7.5. So 7.5 times 1 cubed, which of course doesn't matter, 12 divided by 12, plus the area multiplied by 0. Right, so I don't worry about this in this case. I explain that one more time. This distance of the centroid of the individual shape of A1 to the centroid of the total shape is 0 because we're dealing with the x direction, right? So we're dealing with dx here. So that would be the distance in the x direction, and that is 0 actually for all elements here, for A1, A2, except for the triangles. So you understand that. I can move on to the shape number 2, which is base times height cubed. And in this case, it's 1 times 6 cubed divided by 12, plus the area times 0 again. Same effect. I don't have to explain that again. But now we're dealing with the triangle, and that will become a little bit more interesting. So what is the base now? The base is 1.5, 1.5. The height is 2.5 cubed divided by 36, plus my area, 1/2, 1.5 times 2.5. And now the distance. What do I need? Technically, I need two distances, the one from here to here and the one from here to here. But keep in mind that my distance is squared anyways, right? So if it's a negative number, which it would be here for A3A, if it is a negative number, I square it and it becomes positive, which makes it identical to the one here on the right side for A3B. So I only worry about one, but let's take A3A. And so what I need is 1/3 of the base, which is 1/3 of 2.5, and then add 0.5 to it. And that would be my distance. So I open my bracket here and I have 2.5 times 1/3, right? So 2.5 times 1/3 plus 0.5. And that needs to be squared. I cannot forget about that. And this whole thing exists 2 times. And I want to zoom in real quick just so that we understand what's going on here. So what I did is I took the distance from here to here, which is 1/3 of 2.5, and then I added 0.5 to here. So that is my distance that I'm using for this calculation. And now take a look at this entire structure and notice that much more material is removed from the centroid in the vertical direction, which is what we calculated here, whereas in the horizontal direction, a lot of material is much closer to the centroid, and therefore you will find that the result needs to be much smaller than this. In fact, if you calculate this out, you should find that your IY, and again, please type this into your calculator to get used to those calculations, 26.53 inch to the 4 is your answer here, which is significantly less than what you have calculated for IX. So now I encourage you to calculate problems like these. I think we have deciphered it, and we took the next step to include actually our triangles here. And we also have a better understanding now to the centroidal distance, because we have them removed here in the y direction and then here in the x direction. And that should give you an insight on how to calculate IX and IY in any scenario, because this concept remains the same. Of course, you may end up with different shapes, which then has an influence on this component, or I guess I should say about on this component here. But the concept remains the same. And so I don't think there's a lot of value here in me running more problems with you. Now it's a question of you repeating this. Of course, I'm going to give you a little bit of a hint for the next problem, but overall, I think we have deciphered the moment of inertia, how to derive the equation and how to apply it. And I wish you good luck with your homework on that. And I think you now have the tools you need and that you can do it. And good luck. So here we have a wonderful educational example of a steel plate in which you are asked to find the moment of inertia about the x-axis and the y-axis. And I will not solve this for you right now, but I will give you some hints so that you have the tools to check if you're correct or not. And I will also emphasize the wonderful educational experience that you can get through this. First of all, you have circles in here, so it gives you a chance to actually apply your knowledge about circular holes from a moment of inertia standpoint. In addition, these are holes, so you can learn how to use the subtractive method. And then what you see here, you have actually 4 holes, but if you imagine that there's a horizontal x-axis and a vertical y-axis, then you will see that 2 of the circles actually are removed from the centroid and 2 of the circles are actually close to the centroid. And so what that means, so let's say I take the moment of inertia about the x-axis here that I just drew for you, then you will find that these 2 blue circles, those are actually, they have a centroid location here and here, and they are removed from the total centroid location, which is right there. However, if I look at these purple circles, they actually have a centroid right there and right there, and so they are not removed from the centroid of the total shape. Another thing you can do with this problem, and I encourage you to do that, is also to calculate the moment of inertia about these axes, right? So you can do it for horizontal. So I'm going to call this here XA and this here YA. So I encourage you to find the moment of inertia first about the horizontal axis and the vertical axis, and then what's probably easier, at least for you conceptually, is the moment of inertia about this axis and this axis. And to do that, just rotate your piece of paper by 45 degrees and it will become much easier, right? And also you will have easier access to the symmetry of the problem. In fact, let's talk about symmetry. So the system is definitely symmetric, right? So symmetric problem. And what you will find is actually that Ix is equal to Iy in this case. And you will also find that the Ixa is equal to Iya. And maybe you will find even something else about the relationship between these two if you solve it. However, so that you can check your results, let me give you the result for my calculation for Ix and Iy. And what I have found here was 1760 times 10 to the 6 millimeters to the power of 4. See, with millimeters, you quickly end up with very large numbers. And again, that is something you should practice and not necessarily develop a feel for, but at least don't doubt yourself anymore when you get these strange numbers. And with that said, I think you have everything you need for this problem. And I hope you are a little bit curious about it and you will try to solve it. Please try your best to compare the two results here, what I showed you with the blue arrows, because you will hopefully have an aha moment if you do so. And with that said, we're done with all the problems, and the last thing that's left for us to do is to take a look at our achievements of the lecture.